In this paper, we introduce a brain-robot control framework for offline EEG-driven intention decoding. We benchmark 11 state-of-the-art deep learning models during real-world Rover navigation. Brain-computer interfaces enable hands-free robotic navigation, but most studies use simulators, few commands, and rarely explore predictive decoding. In our experiment, 12 participants operated a four-wheel drive Rover Pro along a predefined route while EEG was recorded with a 16-channel open BCI headset. A first-person camera feed from the Rover was overlaid with 5 flickering red stimuli, each mapped to a driving command: stop, forward, reverse, left, and right. Although this followed an SSVEP-style stimulation setup, the SSVEP responses were not analyzed. Instead, we used continuous EEG collected during navigation for intention decoding. Participants issued commands through an Xbox controller, while the rover's onboard sensors, stereo vision, GPS, IMU, and light, were synchronized via robot operating system on a Jetson Orin computer. EEG data was continuously collected, labeled with driving actions, and prepared for deep learning-based decoding. We designed a data preparation pipeline to ensure robust and fair evaluation. First, joystick velocities were converted into 5 labels: forward, reverse, left, right, and stop. Each EEG sample was aligned at 0 milliseconds for action decoding and at future horizons up to 1 second for intention prediction. The signals were then pre-processed with the PyPrep pipeline, including filtering, referencing, and noisy channel correction. To avoid temporal leakage, we applied a temporal-aware split. First, samples were grouped by label and ordered chronologically. Each label was divided into smaller temporal chunks, and within every chunk, the first 70% was assigned to training and the last 30% to testing. Finally, we combined and reordered all chunks, ensuring that both train and test sets preserved chronological integrity. Finally, EEG was segmented into 1-second overlapping windows, and oversampling was applied only to the training set to balance the classes. We benchmarked CNN, RNN, and transformer models across all horizons. ShallowConvNet achieved the strongest results, with an F1 of 67% at action decoding and 66% at intention prediction. EEGNet and CNN one-dimension were also competitive, while GRU provided a stable recurrent baseline. EEG Conformer delivered consistent but moderate performance. This diagram shows CNNs maintained stable accuracy as the prediction window increased, with ShallowConvNet leading throughout and GRU and EEG Conformer remaining competitive.